All right, let's continue. So, in the previous discussion, we were talking about system calls, and let's take a look at an example or some examples of system calls in popular operating systems. So, let's start with the Linux operating system. There's actually a man page for syscalls, so you can read this man page. So you see here the list of system calls that is supported by the Linux kernel or provided by the Linux kernel. So you have here an example execve, and read, for example, is a system call. So since version 1 of the Linux kernel is already present, the other one is write, okay, the write system call. So this is also also available since version 1 of the Linux kernel. So if we look at the man page, is execve. So you have here the function prototype for execve system call and the description of what this system call does. So I have here an example code, hello.c. So it's a simple hello world program. When we compile it, actually the correct term is build. So when we build this to generate the executable, so we have the hello world output. Then we have a command called strace that will allow us to view the system calls used by that particular process when executed. So as you can see here, we have the execve system call being invoked. We have brk, we have access, and many more. Now, there are a lot of system calls being made here, but we can actually lessen the system calls by making the code by making it static, building it statically, and we can strace it again and have this output. So we have execve, brk, uname, readlink, and write. So the write system call is the one that actually displays something to the screen. So please remember this command strace to trace system calls. So when you run other programs, for example, if you want to run gedit, so you will see that gedit uses a lot of system calls. As you can see it here. So while the process is running, while gedit is running, you see a lot of system calls being executed or called by the process. So that's for Linux. Now let's move on to Windows. So I have the same program here, the Hello World program, but this time we are going to build this in Windows. So I'm using the Visual C++ command line compiler. So type, so this is the code, then you can compile this, then we get the hello world program. Now, to be able to view the API calls and system calls used by this process, to be used by this program, so we can use the API monitor program. So we search for the executable, and then we run it. So it will run the process, and the output of the different APIs and system calls related to the kernel will be shown here. To be able to do this, you have to check this Visual C++ runtime library. So we have a set of functions that will be used to filter. So if you want just system calls, we can uncheck some of the boxes here. And if you just want to filter the system calls, remove this, and then we can monitor a new process, and no system call was made. Okay. So these are the list of functions for the system calls, but in general, you have other APIs wrappers for the system calls used by the Windows kernel, as you've seen earlier. So that's about it for Windows tracing of system calls. So the important thing to note here is that even though we have the same C program, so C is a high-level programming language. When we build this C program in different operating system, build environment or runtime environment, the resulting executable will be dependent on the system calls provided by the operating system, as you've seen in both the Linux and Windows. In our during my undergrad years, we were still using MS-DOS, so we were actually using Turbo C as our compiler for C programs, and the executable generated by Turbo C will have system calls provided by the MS-DOS operating system. Right. So going back to our slide, so this is the example system calls, but we've shown a different example. But maybe we can try this cp command. So what do we have here? So trace cp in the txt out.txt, and you see the system calls associated with I forgot to change the screen, so we trace and we see the system calls associated with or used by the cp command. So normally the system calls are wrapped in the form of APIs. So that's why in the Windows example, the API monitor, when we run the codes, and we run the hello.exe, let's just set this. then reload the program. So you will see here the API column, which is some sort of a wrapper. Okay? So wrapper to the system call. So as a programmer, you don't usually directly invoke the system call, but rather you use the API. So in the case, I actually have here a site, right, which contains the list of system calls provided by the Linux operating system with a link to the source code. And so you can check this out later, but normally the system call will have a corresponding service number that you pass to the RAX register before calling the syscall instruction in 64-bit systems, as you learned in ComSci 131. So here you have the read system call. So man read, you can do this. First parameter is the file descriptor, second is the buffer, and then we have the third parameter as the count. So typically a number is associated with each system call, as you've seen in the previous slide. The system call interface invokes the intended system call in the OS kernel and returns the status of the kernel call and any return values. So you have here the return value. So you just have to the programmer just need to understand the API and doesn't need to understand what the OS what the OS will do as a result of the call. So this is useful when, for example, when writing a compiler. So when writing a compiler, for example, when you are writing to compile the Hello World program, all you have to do is to understand the API for the right system call so that you can generate the corresponding code for that. So we have a runtime support library, which is a set of functions built into the libraries, which is included in the compiler. So in Microsoft, we have MSV CRT, Microsoft Visual C++ runtime library. Okay, so I have here some examples. So I have here Wine. So if you've used Wine in Linux before, so normally when using Wine, when you want to run Windows executables in Linux, you can use the Wine project. Okay, so normally the binaries generated for Linux will not be able to run in Windows because they have different operating system calls. Okay, so they have different system calls, but in Linux you can directly run .xs from Windows using the Wine environment, because what they did is to emulate some of the system calls provided by, or some of the API from Windows. They re-implemented that in Linux so that they will be able to execute programs, Windows programs in Linux. So I did this before. I was able to run Microsoft Office in early versions of Fedora and Ubuntu using Wine. Okay. I don't know the other way around. I don't know if Windows will allow the execution of Linux executables, but we have subsystems like Cygwin to do that. Okay, so the relationship between the API, the system call, and the OS. So as you can see here, I have already made the markings So for the user application, we have hello.c, and API, we have glibc for Linux, we have msvcrt for Windows, and then the operating system can either be Windows or Linux. So if you're building a Windows executable using the Visual Microsoft C compiler, C++ compiler, so you need hello.cm msvcrt. But if you're building the Hello World program in Linux, you will need hello.c and glibc, and then the compiler will generate the corresponding executable with the correct system calls for the target operating system. Normally, the computer architecture, the hardware architecture is also important when implementing system calls. So when you invoke system calls, it will require some parameters to be passed to the system call. So remember that the system call will execute in kernel mode. So how do you pass data from user mode to kernel mode? So there are several approaches. The simplest, of course, is to pass the parameters via the registers, or if you have a large chunk of data to pass to the system call, you may need to use a pointer to a block of memory, or you can actually use a stack, which is part of the machine architecture. So 3 ways: registers, a pointer to a memory block, which is also passed via a register, or using the stack. Now, the main limitation of using registers is that you have a limited registers have limited size, so you will not be able to pass large chunks of data. So this is an example of parameter passing via a table. So you have the parameters, a pointer to the parameters, you load that to the register, and then the operating system will use the parameter from this table and invoke the system call. Okay, so we move on to the types of system calls. So we can actually group system calls along different categories. The first category are process control related system calls, which includes system calls for creating processes, terminating processes. Again, processes are running programs in execution, so we have system calls for that, like fork and exit or kill. For loading and executing, so we have exec and the variants like execve, wait, and other process control related system calls. So each operating system will have to implement some of these system calls. For file management, we have system calls for creating files, opening, closing files, read, write. Okay, so read, write. Okay, we have this in Linux, get and set file attributes. Also, we have system calls for device management, like request device or release a device. And one of those command system calls is ioctl. So ioctl is the code for let's check the man page for ioctl. Usually it's IO control. Okay. So ioctl, which is used to control the device. So the STL system call manipulates the underlying device parameters of special files like terminals, etc. So the operating system should provide system calls for device management. Information maintenance, so we have system calls for getting the date, setting the date, okay, and time, okay, and other information related functions. For communications, we will learn later the different communication mechanisms for processes, inter-process communication. So there must be some system calls for that, like sending messages, receiving messages. If you're using a shared memory IPC, inter-process communication, so you also need to have system calls for that. And of course, protection, like chmod, chown. Okay, so these are system calls that allows you to access protection mechanisms, set or access protection mechanisms. Okay, so this table here describes example of Windows and Unix system calls for the different categories. So you see here process control, we have fork, exit, and wait. For file management, we have open, read, write, close, and the corresponding Windows equivalent, Windows API equivalent. And then device management, so I mentioned about IOCTL, set console mode, write console, read console, information, get process ID, alarm, sleep. Okay. Communication, we have pipes, shared memory open, and memory map, and the corresponding Windows API for that. And protection, chmod, UMAS, chown, and the corresponding equivalent for Windows system. So an example of pipes, for example, ls vertical bar. So these are actually two processes. ls and wc are two processes when executed in this manner. And what happens is the output of ls becomes the input of wc via pipes. So you can trace that as trace ls minus l, for example. So you see the system calls for that command line. Okay. So read, write, sorry, I forgot to repeat the process. Okay, so using pipes. Okay, so this is one process and this is another process, and we can check the system calls used in this command. So you see the mapping of the system calls, so we can we're not able to grep the pipe, but there should be some pipe somewhere in this code. Okay, so the standard library, so C programs invoking printf library call, which is part of the glibc, we will call the write system call, as you've seen already in the strace example. So this is what happened. Printf greetings, you have the C standard library, glibc in Linux, and then it invokes the write system call, and what gets displayed is the message parameter. this is what that figure wants us to know. Okay. So in the execution of programs, so this slide is related to process control. So this just illustrates different ways of executing process mechanisms. So in the case of Arduino, so probably some of you have played around with Arduino. It's a single tasking system. There's no actually operating system. Most microcontrollers or small devices don't really need an operating system. So in the case of Arduino, there's no operating system. Raspberry Pi, for example, uses Raspbian, which is an operating system. So Raspberry Pi is more advanced compared to Arduino. So in Arduino, we have the programs called Sketch that are loaded via USB to the flash memory of the Arduino. So we have a single memory address space, and then you have a bootloader program. So once you've loaded your Sketch on the memory and you boot the Arduino, the bootloader program will jump to that particular memory area containing your program. So that's what happens, and your program will now execute, let's say, accepting inputs from the different sensors attached to the Arduino. For more complex operating systems, like in example here we have FreeBSD, which is a Unix variant, so multitasking. User login will invoke a user's choice of shell. The shell will execute fork system call to create a process, so the typical command line interface. Then we have the exec. We load exec system call. We load the program into the process, and then it will wait for the process to terminate. So I think I have an example, a VM for that. Let me check. Okay, so I have here a BSD program. So I normally download these boxes from OS Boxes. So let me start this. So I have here, I am presented with several options here. So I will choose two for a single user system. So the FreeBSD OS will now be booting. And when I press enter, I will be given a shell, okay, shell prompt, and I can check my user ID. And since this is a multi-tasking system, if I run ps-a, I see a lot of other processes or system processes here. And I might be interested to know what my shell is. So there's no environment variable. So these are just the environment variables set for me in this system. And whenever I type a command here, like a process will be created in the manner presented in this slide. So notice that in the FreeBSD example, we don't have a graphical user interface. We only have a command line interface. Most of the use of FreeBSD is in providing server applications. Okay, so for web servers, for mail servers, firewalls, they usually use FreeBSD for those applications. Okay, so we'll stop here for this video lecture.